Saturn should not be making any sound at all. Space is a vacuum. Sound cannot travel through a vacuum. And yet, scientists have captured something from Saturn that sounds like an eerie, otherworldly hum. But there is an important distinction. Saturn is not literally making a sound that could be heard by a human floating beside it. The signal is a form of electromagnetic radio emission, detected by NASA's Cassini spacecraft and later converted into an audible frequency so we can hear what the data sounds like. And that signal may be stranger than most people realize. Saturn has been producing radio emissions for decades, and scientists have studied them extensively. But when researchers went back through Cassini's enormous archive of measurements, they identified a separate class of unusual radio events that did not behave like Saturn's more familiar radio emissions. The signal was reported in a 2022 study, and researchers identified 193 events in the Cassini archive. Some lasted for many hours, and their frequency behavior was different from Saturn's better-known radio emissions. Scientists can determine that the signal is associated with the Saturn system, but exactly what physical process produces every feature of these events is still being investigated. And that is the fascinating part. The signal wasn't discovered by sending a brand new spacecraft to Saturn. It was hiding inside data that had already been collected years earlier. That tells us something important about space exploration. Sometimes the next discovery isn't waiting at the end of a new mission. It may already be sitting inside an old archive, waiting for someone to look at it differently. But the strange radio signal is only the beginning. Because above Saturn's north pole is one of the most bizarre atmospheric structures ever observed, a gigantic storm shaped like a hexagon. A perfect geometric shape is probably the last thing you would expect to see inside the turbulent atmosphere of a gas giant. And yet Saturn has one. The hexagonal jet stream around Saturn's north pole is enormous, stretching more than twice the width of Earth. At its center is a powerful polar vortex, surrounded by winds moving at hundreds of miles per hour. The structure was first observed by Voyager during its 1980 and 1981 encounters with Saturn, but Cassini eventually revealed its incredible detail. What makes it especially strange is its stability. Saturn's atmosphere is constantly moving. Clouds form, storms develop, winds collide, and enormous amounts of gas circulate around the planet. Yet this six-sided pattern has remained remarkably persistent for decades. Researchers have even recreated similar polygon-shaped patterns in rotating laboratory fluids. These experiments show that under certain conditions, rotating fluids can naturally organize themselves into shapes with multiple sides. So the hexagon does not violate physics. The real mystery is why Saturn's version is so enormous, so persistent, and so stable. And Saturn's seasons make the story even more interesting. Because Saturn takes almost 30 Earth years to orbit the Sun, each season lasts roughly 7 Earth years. That meant Cassini had to observe Saturn through changing seasons before scientists could study the North Polar region under favorable lighting conditions. When visible sunlight was unavailable, infrared instruments could still reveal the structure by detecting heat. Then there are Saturn's rings. For most of our lives, the rings have looked like one of the defining features of the planet. But scientists now have strong evidence that they may be surprisingly young compared with Saturn itself. Saturn formed roughly 4.5 billion years ago. Some estimates suggest the main rings may have formed only around 100 to 200 million years ago. That means Saturn could have existed for billions of years before its famous rings appeared. One influential model, developed by Planetary scientist Jack Wisdom and colleagues, proposes that Saturn's rings may have originated from the destruction of an icy moon. The proposed moon, often referred to as chrysalis, may have existed in a relatively stable orbit for billions of years before gravitational interactions eventually destabilized it. According to the model, The Moon could have moved close enough to Saturn for tidal forces to tear it apart. Some of that material may have fallen into Saturn, while some of the remaining icy debris could have spread throughout orbit and eventually formed the spectacular ring system we see today. The model also offers a possible explanation for Saturn's axial tilt, which is about 26.7 degrees. But this is still a scientific hypothesis, not a completely settled fact. Researchers continue to test different explanations for the origin and age of Saturn's rings. And the rings themselves are much stranger than they appear. From Earth, they look like a smooth, solid disk. They aren't. They are made of countless pieces of ice and rock ranging from tiny particles to objects many meters across and potentially much larger. The main rings are enormous in diameter but remarkably thin. In many regions, their vertical thickness is only on the order of tens of meters. That combination is extraordinary. A structure stretching hundreds of thousands of kilometers across, yet incredibly thin compared with its width. Saturn also possesses an enormous, extremely faint outer ring associated with its moon Phoebe. This ring is so diffuse that it is almost invisible in ordinary photographs and extends millions of miles from Saturn. The rings are also constantly interacting with Saturn's moons. Small moons such as Prometheus and Pandora act as gravitational shepherds, helping maintain sharp edges in parts of the ring system. And then there are the moons themselves. Saturn has a huge and diverse family of natural satellites. Titan, the largest, is bigger than Mercury and has a thick atmosphere. But its lakes and rivers are not made of water. On Titan's extremely cold surface, methane and ethane can exist as liquids, creating a strange cycle of clouds, rain, rivers and lakes unlike anything on Earth. Then there is Enceladus. Beneath its frozen surface lies a global ocean, and cracks near its south pole release plumes of water vapor and ice into space. Cassini actually flew through those plumes and analyzed their chemistry. That discovery transformed Enceladus into one of the most important places in the solar system for studying environments that might be capable of supporting life. It also influenced one of NASA's most important decisions at the end of the Cassini mission. But before we get there, Saturn has another spectacular trick. Every few decades, its atmosphere can erupt into a colossal storm known as a Great White Spot. The most recent major event began in 2010 and became so enormous that amateur astronomers on Earth could observe it with telescopes. Cassini watched the storm grow across the planet. The storm developed a vast white cloud system stretching tens of thousands of kilometers through Saturn's atmosphere, eventually wrapping around a significant portion of the planet. The energy involved was enormous. Deep inside Saturn's atmosphere, water vapor can become trapped beneath colder upper atmospheric layers. Over time, heat and moisture can accumulate until powerful convection suddenly erupts upward. When water vapor rises and condenses, it releases heat, helping drive the storm even further. The result is a planetary-scale atmospheric explosion unlike anything Earth experiences. And the lightning inside these storms is extraordinary. Cassini detected powerful electrical activity, with lightning flashes occurring repeatedly during the storm's most active periods. Saturn's atmosphere can produce lightning far more energetic and much deeper within the atmosphere than ordinary thunderstorms on Earth. This connects to another strange property of Saturn. Saturn radiates more energy into space than it receives from sunlight. The planet is not creating energy from nothing. Much of the excess comes from heat left over from its formation, combined with processes occurring deep inside the planet. One of those processes may be helium rain. Deep inside Saturn, enormous pressure causes hydrogen and helium to behave in unusual ways. Under certain conditions, helium can separate from hydrogen and form droplets that sink deeper into the planet. As those droplets fall, gravitational energy is converted into heat. Over immense periods of time, This process contributes to Saturn's internal heat output. And Saturn's interior remains almost completely inaccessible to direct observation. We cannot drill into a gas giant. Instead, scientists have to reconstruct what is happening inside by studying gravity, magnetic fields, atmospheric behavior, temperature and the planet's response to its environment.